All right. So we're going to talk about vectors today, and we've already kind of alluded to what vectors are. We've done so with displacement. Displacement itself is a vector, but distance is not a vector. What was the difference between displacement and distance? What was the major difference between displacement and distance?
Displacement counts negative and positive numbers, but distance is just overall going back and forth.
Good. So displacement, it mattered if I went left or right because it was negative or positive. But distance, if I walk this way 5 feet, I've traveled 5 feet. That's the distance. My displacement would be negative 5 feet. So displacement, the direction mattered. That's what vectors are. Vectors are values, but also a direction with it. How many people have sailed before or been on a boat at some time, right? Okay. So when you're sailing, you talk about directionals usually. You talk about directionals such as northeast, southeast. When you're in a car, you do that as well. The direction that you're moving in matters. You can't just move arbitrarily 500 miles. You don't know where you are. You need to know if you're going southeast at a different bearing, pretty much a different angle what you're going toward. If you've ever gotten off the subway before, what do you notice at the exits? What do they all say? If you're at a subway that you can exit on both sides, hypothetically, what do they always say? Northwest, northeast, yeah. Directional, knowing which corner you're going to. So today we're going to talk about vectors. Vectors are pretty much something with a number, we call that a magnitude, and then a direction also. So not just 5 feet, but 5 feet north, or 5 feet east, or 5 feet west. So we've already talked about vectors inherently in chapter 3, but we're going to really study them a lot now in this chapter, chapter 4. So we'll start today with those. We'll talk about components of adding and subtracting, and then we're going to get into some trig in this section also. So we did the trig in the summer review packet a lot already, but you still need to know your basic right triangle trig, SOHCAHTOA, all those different things. So we're going to see that in this section to give you a little preview. So let's start first. This is what I was talking about by definition. So a vector is a quantity that has a number. Magnitude means number. So for magnitude, if you want to write down number or value, magnitude is the value or number. And then also a direction. Also a direction. A vector is drawn with an arrow. A vector is drawn with an arrow. Specifically, when we talk about the vector, we talk about the tail to what I went to high school was called the tip. Okay, this was the tip and this was the tail. Your text, I think, uses this image, or I got it from your text, where it's tail and then the head of the vector. Same thing, tip or head of the vector. We're going to use something later called tip-to-tail method, and I'll explain that in a moment. But head and tip are the same thing. You can replace that with that word. The magnitude is simply how long the vector is, the length of it. The direction is the angle, really. So the direction is where it's headed. And usually we give directions with respect, God bless you, with respect to the horizontal. So the angle theta right there, that's like my directional, really, theta. So that's the angle that I'm going toward, my bearing, my directional. Let's go and look at this example A and B together. Whoops. Adding vectors graphically first. So take a look at this example here. If I've got two magnitudes, and I think about it this way, this is like the following, okay? You're here on the side of Central Park. We're going to do an example in Central Park in a little while. But for now, just for this diagram. You're here on the side of Central Park, and you go towards, say, the northern part of Central Park. You have a picnic, you have lunch here, you stop for a little while. Then you come out on the east side, you end up over here, and this is where you end up at the end. If I wanted to add, mathematically, add vectors, the idea is that I take the tip of one of the vectors and begin with the tail of the other, continuing, making this my sum right here. So you're seeing it on the board here in red, okay, in the overhead. In red, that's the resultant. We call that the resultant. So if I'm adding vectors, let's call this vector A, call this vector B. If I wanted to know what the sum of vector A and B is, we call this the resultant here in red at the bottom as the sum of A plus B. So it's a little bit of geometry, obviously, right? You've seen that these are like, what did you call these in geometry? You didn't call them a line. You didn't call it a line segment. what was it called when it had only one arrow at the end of it? Yeah, it was called a ray. But a ray extended forever, right? So these are actually really just line segments. Imagine line segments being summed together. In geometry, you talk about segment addition postulate, meaning if I have two segments next to each other, I can add them up to get an overall segment. It's common sense. Move 5 feet, move another 3 feet. How far have you moved? 8 feet, right, if it's in the same direction. But now we're going to look when it's not in the same direction. So vector A was angled up and to the right, in your perspective, right? Up and to the right. So north, east was vector A. What was vector B, though? Vector B is not northeast. Which way is vector B angled? South. Still to the right, which is east. So southeast. So vector B goes southeast. And the way I can think about that is by drawing my directional with a compass. North, south, west, east. If I look at the direction of angle or vector B, simply draw vector B from the origin of the compass and think about what it would look like. If I drew vector B would look like that. So I can think of this as being southeast because I'm in the southeast quadrant. It's like being in the fourth quadrant on a Cartesian coordinate on your XY axis, right? This is really just the fourth quadrant, which is southeast. That's the direction vector B is pointing. Vector A I'll draw in red. Vector A is pointing this way. So vector A is in the northeast quadrant. So my directional matters based on the quadrant if you visualize it this way. Based on the quadrant, it would point toward. Now, when I sum them, though, I have to literally just connect the two. So I start with vector A here. I start with the tail of vector A. I draw vector A up until its tip. Then I continue with the tail of vector B, and I draw vector B right from there at the angle that it's shown, which is right here. And that's my ending point. I connect my starting to my ending to get the resultant. Now, if I visualize,
Just what happens if the vectors are pointing in opposite directions?
They would cancel each other out. That's a great question, yeah. So if I had something like this, where A was like this, and I summed with that B, and B is a shorter vector, hypothetically, if A's length was, say, 7, and B's length was 2, the answer would be 5. Because it would be a positive 7 like that, and then you go back 2 from there, and you would end up right here at that dot. So the overall vector resultant would be in red right here. Okay, that's how you would addition or sum them. But we're going to see vectors that are not usually along the same line. They're usually at some sort of an angle. And to add them, we just connect them and then go from beginning to end, and that's called a resultant, which is capital R. Now, usually you're going to see in textbooks an arrow above all of these. Because I'm drawing a vector diagram, I didn't draw the arrows. They're not really needed. But when you list a vector, you put an arrow over it usually. And that just means that it has a direction and a magnitude, not just the magnitude itself. So vector A might be 7 centimeters. Vector B might be 10 centimeters. I can't just say 7 plus 10 is 17. Clearly, they're not in the same direction. So R is not just the sum of those two mathematically. So let's go into the next few parts to see how we're going to work that through. So let's take a look at this vector addition diagram. And this is what we were literally just saying. So step 1, if I'm adding vectors A and B together, is to first start wherever I want. So start here and draw vector A. Then I start at vector A's ending point, which is called the tip. Then I start with the tail of vector B and go all the way up to vector B's tip. Then I go from the very beginning to the very end and measure the length of R. Now, anybody have any guess as to how I can figure out R when I have it on a grid like this? What do you think? Use your context clues. How can I figure out the length of vector R by using this graphical approach? We're going to do it with math, and with sine and cosine and all that stuff for sure. But I'm asking you now, how can I figure out the length of vector R? Slope, okay. What do you mean by slope? Slope gives me the direction. I want the length. So slope will be useful for direction, so hold off on that. But I'm asking about the length of vector R. How could I figure it out? How'd you figure out the distance between 2 points on a graph? How do you find the distance between 2 points on a graph?
Subtract them.
Can't subtract them. If they're like only horizontal or only vertical, you could subtract components, but this is at an angle. You could use the distance formula. Do you remember where that comes from now? Where does the distance formula? The distance formula is the following: d equals square root of x2 minus x1 squared plus y2 minus y1 squared. That's the distance formula. Where does that come from? What does that sound familiar to that you learned about in geometry? Yeah?
Quadratic.
Again, square root of something squared plus something squared. When did you have something squared plus something squared in geometry?
Pythagorean theorem.
Yeah, Pythagorean theorem. The Pythagorean theorem is a squared plus b squared equals c squared, right? The resultant, isn't that just the hypotenuse, if you think about it? What would the triangle look like here that gives you r as a resultant? What's the base and what's the height? Tell me what to do, James. Go ahead.
Would you draw the bottom of R,
So from right here, I agree.
the line to the right, and then from the top of R line down?
Yes, and see where they meet, right? So James is completing the triangle here. He's saying, you know what? I can do that. I can go to the end of R. I can do this. And theoretically, don't I have a right triangle now? Does everybody see the right triangle that exists? Here's the right angle right here. There's a right triangle where R is the hypotenuse, isn't it? So if I wanted to, I could just count the boxes along the horizontal. I'll call that for now delta x. I can count the boxes on the vertical. I can call that delta y. A or B, same thing. I could say delta x squared plus delta y squared equals r squared. If you want to put them in parentheses so you're a little bit more clear, that's fine also. Again, the distance along this axis, both sum, both squared and then sum gives you r squared because of Pythagorean theorem. So this is a method that we're going to use called the graphical approach, where you can physically, literally, count boxes or figure out this distance across. Okay, now what's really kind of interesting, and watch what I'm going to do now, just watch. I can make a little triangle for vector A if I want to. See my little triangle there? With a right angle. I can make another triangle for vector B if I wanted to. There's my right angle right there. And theoretically, look, the base of A and the base of B of those triangles adds up to what? What variable or what term or what saying here? What would the base of this plus the base of this equal?
Base of R.
Yeah, which is called? Delta x. And what would the height of A plus the height of B give you? Instead of the base, the height. Yeah, it would give you this entire length, wouldn't it? If the height of this is 2 and the height of the blue one is 8, 2 plus 8 is 10. That's what delta y is. So in a little while, we're going to start breaking up our vectors into what we call components. The horizontal and vertical component. This, take a look. This is the horizontal component of A. This is the vertical component of A. This is the horizontal component of B. This is the vertical component of B. So we're going to break things into components also in a little bit to help alleviate some of the problems we're going to come up with. Okay, but this is the general approach that we're going to take. I want you to visualize first. Let's get into a little bit of math now with this. So let's look at the first problem here. This one is rather easy. We'll start with an easier one, then we'll get more difficult ones. So a person starts to walk and then travels, a person starts to walk and travels 0.4 miles north, before stopping for a sandwich. Then the person starts to walk 0.2 miles east, and then breaks to read a book in the park for a while. After this, the person then travels 0.7 miles south, and then another 0.6 miles east. Graphically determine the person's final location with respect to the starting point. So these are a bunch of vectors, that's all they are. And I was nice here. I made them vectors that were all either up and down or left and right. For now, nothing at an angle. We're going to start with the easier version of this. So if I'm looking at this, okay, let's pick a corner to start, and let's think about these grid lines. What should I make each grid line worth? What do you think? What should I make the value of each grid line based on this problem? Look at the numbers. Tell me what the grid lines should each be worth. What do you think? What do you think, Isabel?
0.1.
0.1. I think that's reasonable, right? If my numbers were like 7 and 6 and 5, then each grid line would be a mile. But because the numbers are pretty small and they're on order of tenths, let's make the grid lines tenths. Okay, so let's pick a starting point. I know we're going to go up, right, down, and then right again. So let's start somewhere in the bottom left. Okay, let's start somewhere in the bottom left. And I know I'm going to go down a little further, so I'm going to give you a hint. If you start too low, it's going to go off the grid line for this one. So let's just start here for now together. Let's all start here. Okay, I'm going to pick something that's in the bottom corner because I know I'm going up, I'm going right, I'm going, up, right, down, and then right again. So up, right, down, and then right. So I'm going to end up somewhere over here in this general vicinity. So make that your starting point and literally just draw your 4 vectors in order. Start with the first one, going north, then go east, then go south, then go east again. So draw your 4 vectors, connecting them the way we did with only perpendicular lines.
And why don't we start at 0?
So you can start wherever you want. We're going to call this the origin for now. This is not an XY axis. This is just a grid.
Okay.
So there is no 0 here, actually.
Okay.
That's the answer.
Okay.
If I drew an XY axis and I want to start at 0, that's a reasonable thing to do. But I'm not even calling this is just a grid line.
Okay.
So if I want to go 4 or 0.4 miles north, I'm going to go to here. That'll be my starting point. So I start here and I go ahead and I walk north, 0.4 miles. So there's the first vector that's drawn. Then the person walks what looks like 0.2 miles east. That's the second vector right there. Then the person walks 0.7 miles south. If you have a straight edge and you want to use it, you probably should. Okay, I don't have one on here right now. Especially with the resultant, it should be a straight edge actually though. And then finally the person says they walk another 0.6 miles east. Ending right here. So this is just a grid line, right? You've done this before. Where do you do this all the time? In the city. You walk a couple avenues east, a couple avenues north, a couple blocks north. Maybe you stop somewhere, get food, go to meet friends somewhere west of there. So you do this on a daily basis, whether you realize it or not. This is pretty much New York City. New York City was made on grid lines for a reason, so that you have some sort of a bearing or reference point. I want to know, graphically, the person's final location with respect to the starting point. What does that mean? Final location with respect to the starting point. How far from the starting point? And vectors. How far and its direction. Okay? So let's connect beginning to ending and call that R. Let's connect beginning to end and call it R. That's my resultant right there. So resultant vectors are really just displacements. That's all they are. Think about it. The distance traveled here would be the entire path in black. Distance traveled is the path taken. So if you sum together these numbers, 0.4, 0.2, 0.7, 0.6 is 1.9. So the distance traveled for this problem, distance, is equal to 1.9 miles. But the displacement is not. The displacement is the length of vector r. Remember, displacement is how far you go from beginning to end, not taking into account the path you travel in. So the length of that vector r is the displacement. How can I figure out length of r? What do you got, Chris?
You can get the base and the height and measure and count the grass.
Very good, Chris. So get the base and the height. So Chris drew in what I just drew in blue there. The base and the height. So think of the original and the ending as always your hypotenuse. And right away, draw a base and draw a height. Chris, did you get a number for it?
Yeah, I guess.
7.7? So to do that, Chris recognizes that this is 0.3. And this is 1, 2, 3, 4, 5, 6, 7, 8. There's 8 boxes there. And that's 0.8. Be careful. Did you use those numbers, Chris?
Yeah.
0.3 and 0.8?
Yeah.
And you got 0.7?
No, 7.7.
Oh, 7. Well, that's way too big, I think. Well, because I'm using 0.3 and 0.8. They're decimals, and I'm going to square them. So my answer is going to be bigger than 0.8 for sure. But 7.7 is really large, right? That's bigger than my distance traveled, actually. It's got to be less than the distance traveled. So just check the math. You're on the right track. You did it all right, but just check the math that you did there. Okay, so if I'm looking at this, I would say this person's displacement would be found out by doing 0.3 squared plus 0.8 squared, and that equals r squared. And I would solve this for r. Again, a squared plus b squared equals c squared. It's just Pythagorean theorem. That's all we're doing here. Can somebody give me an answer for this one? Isabel, what do you got?
It's like 0.85.
0.85
Yeah.
approximately? Yeah, 0.85 approximately? You're rounding, I'm assuming that's what you're saying, right?
Yeah.
All right, so that's the length of the vector r. It's the length of it. How do I find the direction? With respect to the starting point, the direction. With respect to the starting point. What do you think, generally speaking, it is, Rich?
Like when you go north, you're adding here, it's plus displacement, and then when you go south, it's minus displacement. So if you add those, so that's like plus 0.4 on top, then.
And then down 0.7, right? That gives you the 0.3. But I'm asking, like, with respect to where you started, where are you now? Are you northeast of it, southeast of it, northwest of it, southwest of it? Where are you physically?
You're southeast of it.
Southeast of it, right? Because if I start here, in case people don't know directionals, you gotta learn directionals just for life, honestly. I can't tell you how many times I have friends in town, from like out of town. And I'm like, yeah, get off of the northeast corner. Northeast corner. What does that even mean? I'm like, oh my God. You got to know directionals in life, whether it's driving. Like, don't rely on MapQuest. Don't rely on your phone for driving stuff. You'll see later in life, you get into a lot of issues with that. So know your directionals. From here, which way is east? Everybody, which way is east? To the right. So if I go this way, it's south of east. Again, that's how I name my directionals. Let me say that one more time. This is the line for east. So that's like my x-axis if I wanted to graph with an axis, right? Like earlier you were saying. That's the line for east, in dashed black there. I am going below that, so I'm going south of east. So my directional is definitely going to be southeast. Okay, Shannon, you had a question?
So is it just like the direction of the water sign?
Correct, the result. Remember, because we're trying to find out not just the length of the resultant vector, but the direction also. Vectors are magnitudes, which is the length, and the direction. But I need an angle. That's the hard part. I need an angle. I can't just say southeast, right? For those that have been on a boat before, you can't tell someone, you know, your bearing is just northeast. What is it? Northeast. Northeast could be here, 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 all the way up to 90 degrees. That's all northeast, right? So northeast is the entire first quadrant. You have 90 degrees of angles to choose. So you can't give a directional such as southeast and leave it that way. I need an angle. I need an angle. What angle do you think I should figure out or try to find here? Remember, my saying is south of east. South of east. So what angle am I sweeping out when I go east and then move south of that? So imagine going east and then sweep out, meaning go south of east. Where's the angle that I'm sweeping right now? Where is it between?
In between east and your line.
Good. In between east and the, what'd you say?
Result.
And the resultant. Again, think about the angle that makes sense. If I'm going southeast, I'm literally going south of east. That's what that physically means. So go east and then move south of it. If I were to do that, I would sweep out this angle right here. That's the angle theta that I'm looking for in this problem. Okay? Directionals are always given with respect to east or west. It's never going to say east of north. When was the last time you heard, 35 degrees east-north? It's northeast, right? Because it's always either north of east or south of east, or north of west or south of west. You don't say east of north. You're not giving this angle here. You're always sweeping out the angle with respect to the x-axis. This is the angle for northeast. This is the angle here for southeast. The angle for northwest is this angle right here, and then southwest. So it's always the angle above or below the x-axis, the horizontal. Okay, that horizontal line. So that's our angle theta we're looking for. Can you figure out how to get that angle theta? Use your geometry skills. You got a lot of geometry you're going to see in this section. Where else is theta if theta is drawn there? What other angle is also theta? This red and which blue? This blue, number 1 or number 2?
The second one.
This one, right? Yeah, this is also theta. What are they called? Do you remember? Remember your vocab?
Alternate interior.
Alternate interior angles, right? Here's your parallel lines. The dashed black line and this blue line are parallel. This is your transversal. Remember this? Transversal. These angles are alternate interior angles. That is absolutely also theta. So I need the theta that I'm labeled in the diagram, but it's the same as the other theta. So I can call them both theta. These are the exact same things. That is also theta right there. Okay, both of those values are the same. What trig ratio am I going to use to find theta? Well, why tangent? Well,
opposite over adjacent.
good. You could have used this if you wanted to, but I agree with Will. I would use the values that are exact, not a rounded value, right? Because if this was rounded, right? So it is more precise. We'd have to use the more precise answer. We should. I would use the exact values that I already have, so I don't have to worry about sine or cosine using hypotenuse. So I agree. Point 3 is opposite from theta. Use this theta right here, please. Point 3 is opposite, and point 8 is adjacent. So I can write tangent of theta equals opposite over adjacent. So the tangent of theta equals, now be careful with this, opposite, it doesn't matter if you move up or down, the negative doesn't make a difference here. Okay, we're looking at just triangle dimensions. So it's just going to be 0.3 over 0.8. How do I solve for theta? How do I solve this equation for theta? Good, inverse. Do the tangent inverse. Hey, this is something, sorry, this is not pointing you out, Dre, right now, but I'm just going to say it anyway. Something that I want to mention also, try your best, please, to express yourselves with the correct vocabulary. So, because you said opposite or whatever the word is there. Reasoning. I'm grading your labs. And a lot of you did a great job with that lab, the motion detector lab in the gym. I know you understood it, but your wording is so poor that I can't give credit for some of the stuff, even though I know you know what you're saying, but you're not saying it right. For example, this is totally sidetracked. I know I'm in the middle of this, but I got to put it out. I'm in the middle of grading these labs, and I was like ripping my hair out today. A graph that does this. How could you describe that graph in words, in correct mathematical words? What can you say about that graph? Give me something, Joe.
Positive.
No. See, that's the thing. A lot of you right away say, it's a positive. What is a positive graph? What does that mean? A positive graph can mean anything. Is it a positive location? Is it a positive slope? Is it a positive x value? Positive, you see what I'm saying though? It's not specific enough. That's what I'm getting at. Because a lot of the phrases were used like, this is a positive graph, right? And then some people said, but this is a negative graph. It's not a negative graph. It's in the positive region of the axis. It's a negative slope, for sure, right? You see the difference there? Or saying this. Some students said that these were opposites of each other. They're not opposites. What does that mean, opposites? Opposites? They look like they go in opposite directions, okay, but these graphs are, These graphs are not opposites of each other. They're not by any means opposites. The slopes could be, maybe they're negatives or opposites of each other. It's very possible they are not here, but they're not opposites. So let's work on our vocabulary throughout the year. So what I'm saying, I'm pausing now to say this because when you're answering on your labs, you need to answer with coherent statements. Statements that make sense. And if you're not sure how to do that, you need to come ask me for help. Okay, at some point in time, when you're going through it and you're like, I don't know how to express what I'm saying, that's when you can come see me and I can be like, let's talk about this. Let me show you the right vocabulary for this kind of a statement. Because we don't do a good job of verbally expressing ourselves on this stuff. Is that clear? Okay, verbal expressions. In this whole discussion in the math department today, because we were talking about graphs and like you need to be able to interpret graphs well, but also explain what they mean really well. By the way, you could also have just said, this is an increasing function. This is a decreasing function. So that could take the place, Joe, of positive and negative, right? You could say this is increasing instead of saying it's positive. It's increasing, literally, but it's not positive. Because if I extend this graph, down here it's in the negative domain, right? Yeah. It's in the negative domain and negative range. Here it's in the positive domain and positive range. So those words are too generic. You're just throwing them out there. We need to be more specific and clear about what we're saying. So here, again, we use the inverse tan. What do we get for this? What's the angle come out to be?
It's about 20.56.
23? 20.56, approximately. So if I were to give an overall answer, I would say that my resultant vector, notice I put the arrow here, and I didn't put it over here. Take a look, please. I did not put an arrow here, because what am I getting here? Is this the overall vector? This is just the what? Good. It's just the length of the vector. The length of the vector, not distance. The length of it. And this is the actual direction. So my overall vector, when I'm giving a final answer, has an arrow over it. And I say the following. It's 0.85 miles at 20.56 degrees southeast. So this is your schema, your template, the way you're going to do all of these kinds of things with your answer. Vector length at some angle, then the compass direction. Is that clear what I'm saying? It's always going to be answered this way. You always give vector values or vector lengths and directions in this fashion. 2 miles at 25 or 35, northeast, whatever it is. Okay, but this is the general scheme that you're going to follow throughout this entire section. Okay? All right. Let's keep going. Let's keep going. Questions so far? Nothing yet? Okay. Good, good. Do I want to go any further with that question? Mention anything else? No, I'm going to keep going. All right. This is another fun fact. You know this from math already. Addition is commutative. Vector addition is also commutative. And take a look at the example. You can see it's very obvious. If I do A plus B, look at the top one. You do A's arrow first, and then B's arrow, and you end up with this resultant, right? But what if I do B first, and then A? Take a look at the resultant. Aren't the resultants absolutely identical? Whether I do B first or A first, it doesn't matter, which means I could switch the order of addition with vectors. Okay, vector addition is commutative. This could be very useful if you want to add things in a different arrangement for some reason or another, which you're going to see, and you have to change the order in which you're adding the two. Let's do one more. I'm going to add an example. We don't have one here. I'm going to add an example. So I'm doing this in 2 days or 2 periods. I'm going to go a little bit slower here. So let's say the example was the following. Let's say the person first travels 5 miles east, then 2 miles south, then 3 miles north, then 1 mile east, and then 3 miles west. In that order. Okay, in that order. Remember, the order doesn't matter really, right? We just said vector addition is commutative. So the order doesn't matter. But just to be consistent for today, for all of you, draw it in that order. Okay, so draw yourself a sketch. Draw yourself a sketch. It doesn't actually have to be on a grid line. You're going to realize that. You don't really need grid lines to do this. I did it the first time so you can count. It makes it easier. But start somewhere and draw yourself a sketch. Maybe start like right here so you have a little bit of room to move in every direction. 5 miles east. And make them reasonable, right? So if that's 5 miles, make everything... Actually, that's too small. That's my longest segment, so I'm going to make that a little bit longer. 5 miles east. 2 miles south. 3 miles north. This is going to be tough to draw, but watch what I'm going to do. Use another color. 3 miles north right there. 1 mile east. And then finally at the end, 3 miles west. And then here's my resultant. This is a 5, by the way, this first one. Okay, so go 5 east, go down 2 south, up 3 north, 1 east, 3 west, ending right here. There's my resultant. Can we figure out the dimensions of the triangle needed to find this resultant? Can we figure it out? We definitely can. I'm saying, can you figure it out? What do you think, Joe?
Well, the bottom part, like the base side, has to be 1. I mean, I'm saying, 5. Like the kind of like purpose horizontals, like 5.
This is 5 right here, yeah? Okay.
Yeah, and then
what is this?
that would be 1.
So that makes it how much?
So that makes it 6.
And then come back.
Okay.
So what is this going to be? What length?
So I need like
Go 5 over, 1 over, and then 3 back.
so that'd be 2.
5 over, 1 over is 6. Take away 3,
Oh,
3.
3.
Okay? So what I want you to see is physically what you're doing here. I'll actually use another color. I got no colors left. Hold on. I'll use gray. That's the base that Joe was just pointing out. And here's the height right here. There's the triangle that I'm talking about in gray. Let me zoom in on this so you guys can see this better. So this part right here, this base here, is going over 5, over 1, which is 6, and then back 3. So this gray base has got to be 3. Look at all of your east and west only. Don't look at your north and south right now. Only look at your east and west. Does everybody see how the base should be 3? I'm not seeing enough like nods or anything. Are we all clear on this? Yeah? Okay. I want to make sure before I press on. North. What is that vector length, or what is this triangle height right here really going to be? What is the triangle height going to be? Joe got the last one. Somebody else. James has been answering a lot already today. And you answered a question already today. Somebody else, come on. What is the height of this triangle? It's not a difficult question. You've answered a bunch of questions. No, not, I want you to raise your hand. But you've answered a bunch. Where do you go? Go.
1.
Why 1?
Because you came up 3, and there's 2 rounds.
Yeah, so what Rigo's looking at here is this. He's starting here. He went all the way to the right, realized he was still level, right? Then, when he realized I'm still at the same level spot, you go down 2, which is like -2, and then up 3 brings you back to 1. If this were the starting point, down 2, up 3 puts this at a height of 1 above it. So we know that these dimensions are going to be 3 and 1. There's the 1, and there's the 3. So what is this resultant vector in magnitude and in direction? Figure it out, please. I want to know the angle. I want to know, is it north, south, east, west? What's the directional? And what's the length of r? Figure all that stuff out based on the last example. So r should give you the square root of 10. That's what you should get for r. Right? That's pretty easy. 9 plus 1 gives you 10. And the angle? The angle, I'm going to use the tangent of theta. Here's theta right here. Here's theta. Tan theta equals 1/3. So therefore, theta equals the tangent inverse of 1/3. Anybody got it? Yep.
18.43.
So my final answer will be this whole thing. You can start packing up. Will be root 10 at 18.43 degrees northeast. Okay, northeast. That's the resultant vector for this problem. Now, listen, tonight, I'm going to see you guys tomorrow. We're going to continue this. You can practice this tonight. Do you see how I just made up that example arbitrarily? Do the same thing. If you do not fully 100% get this, practice it after school today or tonight on your own. Pick arbitrary lengths and do it. Okay? If you want to get a head start on the problem set, you can do that too. So here, we have to take a look at our vector components first. And I talked about this yesterday. I talked about how if you have the x component and the y component, you can always find the actual resultant using Pythagorean theorem. Because really, you're just looking for the third side of the triangle. So in this case, what we want to do is we want to start talking about x and y components and come up with them trigonometrically. So what trig ratios can I write based on this diagram? Using these terms, or using instead, I can use x here, and I can use y here, and I can call that r there. What are my statements I can make for the trigonometric ratios? Give me one of them, right?
Tan of
Theta.
not the symbol, so
Theta.
theta is vector A over the vertical component
Over.
over the vertical component.
So we have, this is opposite, right? This is adjacent. And this is hypotenuse. So remember tan? What's tan? TOA, right? Do you remember your acronym? So it's got to be opposite over adjacent. So vertical over horizontal. So instead we can think of this also as delta y over delta x. Now, this is going to be really useful in a little while when we talk, and we've already kind of got into this with the angle theta, but we didn't talk about it in terms of x and y. So for the angle theta, whatever you're going to stop, when you're looking for the angle theta here, in our diagrams, we can recognize it by taking the tan inverse, and we can see that we can always use delta y over delta x. This is the angle of the resultant vector. This is very useful to use. Yesterday, we didn't write it out in an expression algebraically. We wrote it out numerically. We used the numbers that we had there, and we did tan inverse to get the angle theta. But this is a good method of getting the angle theta by itself. So that's the first part of vector components. Give me another one of the ratios, and we'll go over the other two parts. Vertical over the vector, or let's call it vector for now. It's fine. So in this case, we could say the vertical is the delta y over the vector length itself. Good. And then cos theta, we'll talk about these together in a minute. Cos theta is, go ahead.
Horizontal overhead the vector.
Very good.
Sorry.
So adjacent over hypotenuse, or delta x over the vector. All right. So what we need to do is we need to think about these lengths and determine what the horizontal component is and what the vertical component is. And the reason we're going to do that, and if you think back to the diagram the other day, when you add things graphically, say I have two vectors connected. I can just connect the base and the height, and then the other base and the height. And remember how we added them together? We can do that now if we can break a vector into its other components. We've been designating the components as delta y and delta x. Horizontal component, I'm calling delta x right here and right here. Vertical component, I'm calling delta y. So if we look at this, we want to take this part of the equation right here and figure out what the horizontal component is, and here, what the vertical component is. So solve for delta y in this equation. Forget this piece in the middle, this was just a description for a minute. So solve for delta y and solve for delta x, ignoring this piece right here. Okay, solve these two equations right here for delta y and delta x. And those are the values that we're going to use all year. If you look at your formula formula sheet, that's the first thing written on your formula sheet, actually. Okay, so when you're done solving for those, definitely do that. Open your formula sheet and try and find that on there. Again, if you're not going to calculate anything here, just go ahead and solve, as you see here, for delta y and delta x. Okay, solve for those two variables, just multiplying by the term vector on both sides. So how could this be useful? How could this be useful? In a minute, we're going to add vectors together, but I want to give you a quick idea of application, why you're learning this before you even go into it. So, if I think about the problems we've been studying so far, what directions have the displacements and velocities been? They've only been what and what? What directions are these? What and what? Left and right, or up and down. But as I walk, is my body only going left or right? What's also happening? Kind of like naturally your body moves vertically slightly. Like you're gonna kind of move your shoulders a little bit. Your body itself gets lower when you step, gets taller when you come back, it's lower, you know what I mean? So there's actual oscillations up and down also. So things don't just move vertically and horizontally, is what I'm saying. Things move at angles. Think about anything where you involve a sport with an object or you throw an object, it's always going to be at an angle. You never throw a perfectly horizontal, well not, I shouldn't say that. Some pitchers, the ball doesn't even drop at all. But it does drop on a level that's probably like nano-stop. You know what I mean? It's dropping very small deviations. So here we have to think about the fact that we want to break up something that's kicked or thrown or launched at an angle so that we have a horizontal component of the velocity and a vertical component. So if you look, I don't remember, anyone have the formula sheet open if you open it, remember? Do I write it in terms of velocity or do I just say x and y or do I use vx and vy? Okay, so I use r. So I use r for the word vector. So take a look on the formula sheet for that. You'll see r labeled as the vector length. The hypotenuse will say r. This says r cos theta, which is right here for delta x. And for delta y, this says r sine theta. So if you want to figure out those small components, all you have to do is multiply by the right trig ratio, either sine of theta or cosine of theta. Now, we're making the assumption, so write this down. We're making the assumption that theta is always given between the vector and the horizontal. Again, this is assuming, so write down that theta is given between the vector and the horizontal. If it's given up here, it actually switches. These two switch. This becomes cos, this becomes sine. Okay, so if theta is given up here, this is not true. If theta is given up here, what do you just do? Simple math, right? Because if this is an angle of 60, then what would this angle that we need be down here? Joe? It'd have to be 30, yeah. Because this is 60, this is 90, that's got to be 30 there. So if you're ever given this angle, see where I'm pointing? If you're ever given this angle right here, instead, you just subtract it from 90 and get the actual angle you're going to use down here. And then you can use these expressions. Okay, but if you want it to be a little bit, you'll see why in your math course this year with trig, you could also use this angle and just switch the sine and cosine. That works too. Kind of think of it either way. They both work. Let's get into an example of this now that we know this. So remember this diagram a minute ago? Let's take a quick look at this diagram and go step-by-step process through it. So first, we want to add vector A and B together, right? So what we need to do is break the vectors into their components. I'm going to zoom in a little so we can see this better. Let's take a look at the middle one here. So first, vector A was a length of 12 at an angle of 20 degrees. Look at the name of it at the top, please. That's our vector notation, right? They don't put northeast because it's in the diagram. So if you had no diagram, you should specify a directional such as northeast, God bless you, such as northeast, northwest, southeast, southwest. This would be northeast in both cases. So here's your 20-degree angle. Please look up for A right here. We want to break it into its x component so we can sum this with the x component of B. So these are the horizontal components that we just came up with on the last slide. We wrote down a formula that would allow us to solve for this horizontal and this horizontal for each of these two different vectors. And these are the values they'll come out to be. And let's go through the math process to get them. So we're going to get these two numbers. Then what can we do? So you can see, we sum these two values together. 11.3 and 12.5 sums together to 23.8. And that's this overall length. That's the overall height. So if we want the overall vector in the end, we can square these two and use Pythagorean theorem to get r. We can use this as the opposite, this as the adjacent to get the overall angle theta right here. So the process that we're undergoing is just to separate these into little pieces and then put those pieces back together. And it's literally what you're doing here. So let's discuss where the 11.3 and 12.5 come from. It's going to be off on my screen. I got to move over. Okay. So the AX value, how would you get the, based on the last slide, what would I write down to get the horizontal component of vector A? Just literally read the formula for me and just fill in the vector with vector A. So what would I actually do mathematically? Look at your numbers. Your numbers are given at the top up here. I'll point to them so you can see. Here's your values for vector A. Go ahead. Perfect. Go ahead, Isabel.
The vector times cosine theta equals the horizontal, which is delta A.
So tell me vector A. What do we have? What are the numbers? They're at the very top. So the vector length is given first.
So it's 12.
Good. Times the cosine of?
25.
Just 20, right?
Oh, 20, yeah, sorry.
That's okay. You use the degree after that, so that's the angle. Good, very good. So if I want the y component, so this will end up equaling, check it on your calculator. Seriously, do it right now. Type that in your calculator. Make sure you're on degree mode, please. Make sure you're in degree mode. And you'll get this answer here of 11.3. Please verify it, though. Let's make sure this diagram is actually right. So others got it, but I still want you to do it. Everybody do it, because if you don't get it, it means your mode is on the wrong setting, so you can fix that now, right? Sometimes you're going to work with what's called gradient mode. So in your math class, you might have to change back. But for now, have it on the degree mode. What's AY? Now that Isabel really helped us out with AX, somebody else can be AY. There's only one change that has to be made. For the X component, we said to use cosine, right? That was the statement we made. So what's the only change I'm going to make? Agreed. 12 times the sine of 20 degrees. And that should give me 4.1. Check it out to make sure it works. So this is your way of breaking up a triangle into its lengths. If you have given only the angle and the hypotenuse, right? You literally only have the length of A, which is in the diagram. I actually should just write 12 here so we all see it. In case anybody doesn't know, this is where the 12 is coming in right here. This length is 12 right here. Okay, so that's actually the length of 12. And this angle right here is your 20-degree angle. Actually, 20, I can't really draw it, okay? So it's right here on our point. Right, it's the AX, a little angle right there. From here to here, this little arc. For the B vector, we would do the exact same thing. We take the length of vector B, which is 25. So instead of 12, we use 25. And then here, instead of 20 degrees, we use 60 degrees. And do the exact same thing with vector B. So I'm going to quickly do that because this is pretty easy now that we've done it once. So the length is 25 times the cosine of the angle, which is 60 degrees. And then vector, or part BY, vector component BY, is 25 sine of 60 degrees. And those values are given also in the diagram, 12.5 and 21.7. Now, this is kind of important because a lot of people struggle with this concept. Here's the angle 60, by the way, right here. That's the 60-degree angle I just drew in. Okay, right there. That's our 60-degree angle. It's not with respect to this axis we started on. Does that make sense what I'm saying? So when you get to the end of vector A, visualize, look where I'm looking, please. Look where I'm pointing, please. When you get to the end of vector A, this is like your new origin. So this is like your new x-axis, so that's your new angle. Do you see what I'm saying? So when you get to a new location, that's like you're starting over horizontally with a new horizontal, and now the new angle is above that, not above down here. So let's do a problem with this. Oh, I guess we should just finish this one real quick. We have our values here. So the x components can be added together. So I'm going to circle them in green. I can sum those together because that's just this length right here. I'm going to draw it in green. That's this length from here to here. That's the sum of the x components. And I need that length. In the next diagram, you guys already see it. It's 23.8 over here. So that's what I'm doing. I'm adding these two numbers together to get 23.8. And then what am I doing after that? What am I doing after that? I've got the horizontal overall component, Ricky. Yeah. I need to add these two values, 4.1 and 21.7 together to get the overall vertical component. I got to move down. My page runs off. To get the overall vertical component, which is this length from here all the way up to the top. Okay, I ran out. I can't actually go any further yet. So that's the vertical component. We're seeing that along here. That's 25.8. So how do I get the overall vector at the end? What do I do with the legs of a triangle in order to then get the hypotenuse? What do I do with the legs of a triangle to get the hypotenuse? I know you guys know this. Please raise your hands. It's almost kind of sad that it's the same people. Sophie, go ahead. Yeah, you square them and sum them. Pythagorean theorem. So, see, by the way, this is what I see. I don't know why this does this. I get cut off, so I'm having trouble seeing what you guys see over here. 23.8 squared plus 25.8 squared equals r squared. I also want to get the overall angle theta right here. That's the angle I'm looking for. I know the resultant vector will be northeast because the other two are both northeast. There's no way I can add two northeast vectors and get something that's not northeast. This is not logical, right? It's like saying you add two positives and get a negative. It doesn't work. So the answer is going to be at some angle northeast. So let's find theta also. What trig ratio can I write to get theta? I have the legs of a triangle. What trig ratio? Same two hands. I appreciate it, I do. Others know this. What trig ratio, go back to the last slide if you want to, can I write in order to solve for theta? I've used two trig ratios already. There's one trig ratio left. Perfect. So tangent of theta. Now, Fiona, in this case, here's theta. So is 25.8 or 23.8 considered opposite? Yeah, I got to go across the triangle from theta. So this is opposite. So let's put that in the numerator. And the base down here is adjacent. So let's put that in the denominator. And then I remember r is easy to solve for. But how do I get theta? What do I do to solve for theta here? Good. The tangent inverse. So we say that theta is the tangent inverse, which is like, just pretty much means in this case, I don't want to use the word opposite, but you can think of it that way for now. It cancels the tangent function. It gets rid of it. So it gets theta by itself. And then you just do that of that number. So whatever that trig ratio happens to be. 25.8 over 23.8. Yeah.
It comes out to 47.3.
47.3?
Yeah.
Okay, approximately 47.3. And what did r turn out to be? What did r turn out to be in this case? Yep.
1,432.08.
Give me the number without the square root though, right?
35.1.
And this was given with no units, so for now I'm not going to put units. I would put units though if it was like miles or kilometers. So that's my r value, that's my theta value. I write my overall answer as a vector. The overall answer would be r, right here, is equal to 35.1 at 47.3 degrees northeast. So this is the same process we underwent yesterday, right? We ended up coming out with an angle and a length. So we have a direction and a magnitude. But we went about it a different way by using sines and cosines and tangents. You notice the difference? So you see how yesterday was a graphical approach. We broke things down with the picture with the actual diagram. Whereas today we're seeing that we're using this algebraic approach, using some sort of minor arithmetic and algebra and trig all together here. Okay, there's one more I think. Let's take a look at this next one here. So I want you to take a look. Try to diagram it first, and then we'll take a look at this in pieces. This one's a little bit trickier, simply due to the fact that we're noticing that it's not all going to be northeast. So now we have to consider negative vectors. So if the component goes down or left, you should probably do what? Label it as, if it goes down or to the left, what should you label the vectors as? As negative. Think about that right now. So if you want to do it yourself, you get a head start, work with the person next to you. You got a little bit of time, you can definitely do this problem. But draw your diagram first, then check with me on my diagram before you get into the beginning. Okay? So start with the diagram. Check your diagram with the person next to you first too. That works always to start. Check the beginning of your diagram if you got the beginning part done. We're gonna get to the vector part in a moment. But for now, just to check to see. I also like to draw the topics up there. I forget sometimes, so it might be a useful technique for some. You know which quadrant you're going into based on the bearing. All right, like southeast, that's why I went down and to the right. Fourth quadrant. When you're ready, break these vectors into vector components by filling in the right triangle here. And then this right triangle is going to be a little bit funky, but it's going to look like this. Take a look what I'm going to draw here. And I'm going to go down and to the right. So draw the triangle in the direction you would have walked. Like this is to the right and up. This is down and to the right. Okay, or you can go to the right and down. It doesn't matter. But just make sure you complete the triangle up here, not down here. So I'll do X components in blue for now. That's the first vector component. And the Y component I'll do in red. And I'll do the same thing for this one. X in blue. And then Y in red. So think about it mathematically. This is where your geometry class really comes into play a lot. You're going to see a lot of geometry this year. I keep saying that. Look at the red lengths. One goes up, and then the other, what does it do? It comes back down. So you have to think of this as a negative vector when you're summing them together. But the blues, aren't they both to the right? So you're just going to add the blue lengths together. But we actually have to come up with those values So what is this first value? The first blue vector on the bottom, or vector component, I should say. What's the first blue vector component on the bottom there? What number would I use to represent it? Or what expression? I don't want the answer, but I want, like, am I using 0.8, am I using cos 30, sine 30, I'm using 0.5 or sine 25, cos 25. How do I get this first vector component? Come on, we got to be able to do this by now. This should be like, I should have somebody volunteering every 2 seconds. Chris, take a stab. You kind of put your hand up.
I think you do 0.8 cos 30.
Very good, Chris. So Chris, you remembered, you take the actual vector, which is 0.8, and you multiply by the cosine of the angle, which is cos 30. Absolutely right. Good job. How about the red one, Conti? I know you know this one. The red vector length for the first one there. It's the y component. So instead of using cos, use, sine 30. So again, that's the length of this vector. It's always just whatever this is, times sine 30 gives you that. Whatever the vector is, times cos 30 gives you that. We need to do the same thing for the next one. Please do it for the next one. It's literally the same thing. Your angle changes, your vector changes. Besides that, it's the exact same process. And notice what I'm going to do for this last one. This is the only one I'm doing it for. I put a negative sign on this vector because I know that its directional is down. Everything else is bit to the right and up. Anytime a vector points down, okay, if I follow the path, I should put arrows actually to help you guys. Let me put arrows. The vector components should have arrows at the ends to help. If an arrow points down, which this one does at the end, its value is negative. The other arrows point up and to the right always. So I got to add the blues together. If I add 0.8 cos 30 plus 0.5 cos 25, I will get 1.15. That's the overall x dimension of this. Remember, what's my resultant? This is kind of wild, right? Let's draw the resultant in. Here's the resultant right here. That yellow coming across. So this is the base of the resultant. What's the height of the resultant? Take the positive red value, 0.8 sine 30. Add to that the negative, or just subtract it, really, right? Add negative 0.5 sine 25. I'm going to get 0.19 for this piece. Oops. Okay, those are my lengths. Those are my dimensions that I'm looking at in this diagram. I have to take these values again and complete the triangle. Get the vector length r by using the Pythagorean theorem. Get the angle. Look at this little angle right here. That's the angle you need to get. And it's definitely northeast still, just based on looking at the diagram itself. When would it be southeast as an answer? When would the answer vector length be southeast? What would this number have to be? Negative. If your overall y sum of these two vectors turns out to be negative, it means you're down here, which is southeast. If your overall x value were negative over here, well now instead of east, it's west, right? It's west. If this is negative, it's west. If this is negative, it's south. When these are positive, it's north, and positive for this, positive for this is north, positive here is east. You can use the value signs to indicate whether it's northeast, southeast, northwest, southwest. R will turn out to be 1.15 squared plus 0.19 squared, all that under a square root, which is going to be 1.17, and it's in kilometers. Theta, again, if I do theta, theta is the tangent of theta equals 0.19 over 1.15. So theta is tangent inverse of 0.19 over 1.15, which is 9.4 degrees. And that's northeast. So I hope you're going along with this. I didn't go through those last two steps because this is now the third time we've done it. We did it graphically, algebraically, and then one last time, mainly algebraically, but we're kind of using the diagram to help ourselves, right? So this is kind of like a combination of graphically by representing things the way we're doing it. You can do this problem with what's called the table method, where you just find the x components by themselves, find the y components by themselves, by just writing out the equations without even drawing a diagram at all. So if you want to take that exploration, or take that option, I can show you real quick the setup for different few minutes, but I also put one example, I put 3 examples on Moodle from I think last year that I recorded, or 3 separate examples. Either I recorded them or I found them on YouTube, I don't remember, but it's a video I listed there, and I saw it was there, so I'm going to make them visible. So if you want to use the table method, one of them definitely goes with everything with the table method. I think that's another YouTube video that somebody else made. But it's a decent method. A student last year proposed it, so you can use it. I like the visual method because I can see it physically here. But if you like to be quicker and on a test, it might save you time to go with the table route. I'll show you that.
How'd you get 9.4?
I took the angle here, James, which is theta, and I wrote a trig ratio. I have the adjacent length, which is this, and the opposite, which is this. So tangent of theta, this is what we were talking about yesterday real quick. So tangent of theta, this angle, because tangent is opposite over adjacent. I know tangent is opposite over adjacent. From this acronym, I have, this is theta right here, making this opposite. And this one has to be hypotenuse always, it's the longest length, making this the adjacent length right down here. So tangent of theta equals opposite over adjacent. And then you do that second tan thing that we were talking about, okay? Second tan of that ratio. So you can remember the formula too on the previous page, a couple pages back. I'll pause.